Going to talk about the estimation maximization algorithm, and the example that I will put has to do with processes that come from a number of Gaussian mixture models. Let me give you the quick example. Let's assume that in any given day, if the day is cloudy, the temperature is going to be picked at random from a cloudy day temperature probability distribution, right? So if the cloudy day, for example, if the temperature is around, say, 50 degrees here, okay, then I'm going to pick, any temperature around 50 degrees. If the day is sunny, on the other hand, if the day is sunny, then I'm going to pick a temperature from a sunny temperature distribution, this one, right? With this mean, for example, right? And I will pick a temperature here, 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 right? I'll pick a temperature that is highly probable in the sunny day distribution. So if I just assume that temperatures get picked from a distribution depending on whether the day is cloudy or it's sunny, okay, what I can say is that I have two Gaussian, so this k here will be two Gaussian distributions, and each instance, each temperature here is, or temperature reading, is generated by choosing one of the Gaussians, right? So basically, whether it's cloudy or sunny, I will choose the different Gaussian, and then I will generate an instance at random according to that Gaussian distribution. This is the process. This is the process by which, say, for example, two Gaussian distributions affect the temperatures of given days. Another example could be, for example, if you have height, well, whether you're female, you have a distribution of heights, and if you're male, there's a different distribution of heights, right? So the data that can be generated would be generated by saying, okay, let's pick first whether we want to generate data for female or for males, and then randomly picking from the distribution. So let's work on estimating the means with the estimation maximization algorithm. Now, you know that the instances are generated by mixtures because there are two or more. Instances are generated by a mixture of Gaussian distributions. However, we don't know the means of these Gaussian distributions. In the previous slide here, right, in the previous slide, we know the Gaussian distributions, but what if we don't know those Gaussian distributions and we only have the data? Can we determine, we only have the data and we know that therefore, say, females and males, or for cloudy days and sunny days, can we determine the means of a cloudy day and the means of a sunny day? That's the big question here. So we don't know the means, and we don't know which instance was generated from which Gaussian. So the idea here is to determine what's the maximum likelihood estimates of all the means. Because if we know the means, then we know the probability of each day being generated from one or the other Gaussian. Okay? Now, if we think of each instance as having a number, and then a proportion from the first Gaussian, a proportion from the second Gaussian, for example, in the case of two Gaussian distributions, we can think of it like that, right? So where I is the index of the measurement, and 1 or 2 will become j. That's the Gaussian from which they were picked. So we have z of ij, which is basically 1 if the measurement I here was generated from this jth Gaussian distribution. Basically, it's 1 if the measurement came from Gaussian 1. If it's 0 if the measurement came from Gaussian 2, for example, right? So we can say, for example, z of 1, 2, right? This will be 1. This will be 1 if x1 was generated by the second Gaussian. It will be 0 if x1 was generated by the first Gaussian. Now x sub I is the observable data that we have, and we do not know this zij's, right? Which Gaussian generated which distribution, which measurements. So that's the main problem. But again, going back to our intuition, we want to find out what's the mean of a Gaussian that costs some data, and we only have the data. We don't know the Gaussians. The main formula here for this, okay, the main ways in which we determine this is by using the estimation maximization algorithm. The estimation maximization algorithm first picks a random initial means for the Gaussians. I'm going to illustrate here with only 2 Gaussians, okay? And then it will iterate with the E step and the M step. The estimation step, E step, will calculate the expected value of each hidden variable of each number being generated with each distribution. Okay, that's what Zij means. Assuming the current means, right? The ones that I set up here. All right, and the way you do this, you compute the probability of a number being whatever number you observed, given the mean from one of the distributions, divided by the probability of observing this number given the mean for all the distributions. You add these, right? So if we have 2 distributions, you compute the probability of, say we want to compute the estimation of the first distribution, of the data coming from the first distribution. We will go for each data here, okay? So we will compute, the probability that the first number came from the first distribution. Then we will look at the probability the first number came from a distribution with mean mu1, which is this one, divided by the probability that this number came from that same distribution plus the probability that this number came from the other distribution. Okay? Going into more detail, because this joint probabilities are proportional to the density function, this is how we compute those numbers. Okay? So basically we compute the Gaussian distribution. This is the formula for the Gaussian distribution with a given number and a given mean and a given standard deviation. Okay? And a given standard deviation. And then we divide that by the sum of all possible, by this number with this standard deviation, for all possible means that we have, all possible Gaussians. In this case, it's only 2. So we go from 1 to 2. Okay, this is how we compute the estimation that the element I came from distribution J. Okay, so for each number here, each of my numbers, I'm going to have one of these for each distribution. So if I have 10 numbers and I have 2 Gaussian distributions, I'm going to end up with 20 of these E's, of these estimations. Now, the next step is the M step. The M step is the maximization step. We'll calculate a new maximum likelihood hypothesis. Basically, we'll compute 2 new means, okay? Assuming the value taken on by each hidden variable Zij. So we call these hidden variables because we don't know them, we're estimating them. So the idea, the way to compute this is for example, for distribution J, for distribution 1, for example, okay? We will go for all the EZIJs, so for all the estimations for all the numbers with distribution 1, times the number, and then we'll divide it by, we add all those values, and then we divide by the summation of all the estimations of Zij given this J. Okay, so it is important to keep these things right. I mean, there are many structures that can help us in computer science, many structures that can help us keep track of these things. But if you do it by hand, it is very important that you do this. You keep track of what's I and what's j at every given point in time. So let's go through an example. That's the best way to illustrate this. Say we know that on cloudy days the temperature is generally lower than on sunny days. We know that. Both cloudy and sunny days can experience variations of about 10 degrees. So for example, a cloudy day can be 50 degrees or 60 degrees or 40 degrees. That's kind of a cloudy day. Sunny days can be 90 degrees, 100 degrees, 80 degrees. Those are all temperatures of sunny days. So now, given the following temperature for 10 random days, so in 10 random days, say at 3 p.m. somebody took the temperature, and these were the temperatures: 70, 62, 89, 54, 97, 75, 82, 56, 32, and 78. These are in Fahrenheit degrees, okay? You'd be burning if these were Celsius. Now, what's the mean temperature for sunny and for cloudy days? This is the big question, right? So we have the data, but we don't know what does a sunny or a cloudy day look like. What's the mean for a sunny or a cloudy day, right? That's the mystery you have to solve. So the first thing that I do is I set up the problem. So we have sunny and cloudy days, so two kinds of days. So K is 2, okay? Then let's assign a random means to sunny and cloudy days. Let's assume this is just off the top of my head. Let's say 80 is going to be sunny days and 55 degrees is going to be the mean for cloudy days. This is absolutely randomly picked. And then we know the standard deviation for each day is 10, right? This is given. The problem said that the days could vary 10 degrees, give or take. So this is all we have. Now we have a bunch of things, right? So this 10 will become the sigma in my formulas, right? This will be the initial mu1, and this is the initial mu2, right? And this is k. So I have enough to get started. And I have my data, right? I have all my x's, all my data. So all the data was here, right? So this is x1, x2, etc. Okay, till x10 here. x10. Whoop, I'm not very good at this. x10. So this is x, and we have on the other side we have all my x's, we have my mu's, my sigma. All I need to do now is to compute the zij's. Okay? So let's do this. This is the data again. Now I'm going to do the E step with sunny. The mean is 80, right? So what I'm going to do, I'm going to go back to the formulas for the E step and the M step, okay? What I'm going to do is I'm going to use this formula here to compute for each data point. I'm going to compute the probability that of the estimation of z of that data point with, say, distribution 1, which is sunny. So here it is. For sunny, the mean is going to be 80, the standard deviation is going to be 10, we know that. And if I compute that formula, I get these values for each one. For 70 degrees, I get this value. For 62 degrees, I get this value, and so on and so forth. What these values mean in one sense is, what's the likelihood of, say, observing 70 degrees on an 80, if my average is 80, right? If my average is 80 degrees, then 70 degrees has a 65% chance of being one of these days. 62 degrees, on the other hand, has a 20% chance of being one of the 80 degrees. And if we look at the second to last temperatures, 32 degrees has a 0 chance of being a sunny day, right? Now, for cloudy, the mean is 55. I will compute the same formula, only that I will be using this mean instead, right? So remember, in this formula, I have to use mu j, right? So first I used the first mean, 80, and now I'm using the second mean, which is 50. So I compute these numbers, and we see something similar. These would be complementary numbers, by the way. But we see that there's a 35, almost 34, 35% chance that 70-degree day is going to be cloudy, and so on and so forth. And there's like a 1%, almost totally sure that a 32-degree is going to be in the cloudy range, right? So this text tells you how likely is each of these days to be in one of the two distributions. With this now, I'm going to compute the mean of each of the sunny and the cloudy days. So for sunny days, and now let's go back to the formulas again. What I have to do is, for each of these estimates, for each of these likelihoods, right, I will multiply that likelihood to the actual value of the data. I will add all of that and divide by the sum of all these likelihoods. So if I add all these numbers up, I will get 5.7. Okay? If I add all these sunny numbers. Now, what I'm going to do is I'm going to multiply 0.65 times 70, and that gives me 45.59. 0.20 times 62, that'll give me 12.51. And so on and so forth. So this is, I multiply all these values, right? And then I add them together, and I get that the new mean is 81.75. Then I will look at this, right? I will do the same, but for the cloudy days now. With means 55, with this set of numbers now, okay? All the way with this set of numbers, and I will compute the means, and that gives me 53.35. Now with these two means, right, I will go back again and do the same process over. Again, the E step, only that these means are going to change, right? And I will do the same thing, and then I'll do the M step again, and so on and so forth. And I will iterate until the difference between means is less than 0.1. Why? Because I don't care if it's 53.3 or 53.4, it's the same to me, okay? So I will iterate until this means don't change by more than 0.1, okay? That's what I need to do. So, so where am I now? Let's look at what some of these iterations look like. Well, after iteration 2, at iteration 2, I get a mean of 81.79 for sunny, and for cloudy I get 53. For iteration 3, I get 81.77 and cloudy 52.91. So for iteration 2, I got 81.79, which is very similar to what we had before, but I got 53 degrees, which is more than, I had 53.35 before, now I have 53, so this changed by more than 0.1. So then I iterate again. And again, for the sunny days, it doesn't change much. And then for the cloudy days, now it changed by 0.09. So we stop iterating there. And we can say that for sunny days, the temperature is approximately 81.77, and for cloudy days, it is 52.91. We have found the two Gaussians from which these numbers were taken, right? So in other ways, we have found, in this initial picture, we have found the means of these two Gaussians and all we were given were these data points. And that is how estimation maximization works.